Well, hello, physicists. You were right, those of you that were predicting that we were going to have a snow day again this week. Hopefully, this will be our only one, but here, we just got to wait to see, I suppose. So, as promised, I have some physics for you to work on today. I wanted to let you know that I have started to update the new calendar. It's up on Canvas, and so you can kind of keep looking there. There is an assignment to go with the lesson that we're doing today, and I'll just keep updating it as we go. I haven't put a lot of dates in because, no commitments on that since we don't know what the weather will bring. So I did also want to clarify that both the resonance tube analysis, that's what we worked on last week with the tuning forks, and the wave take-home test will be due on Wednesday in class, assuming we have school on Wednesday. Again, no assumptions are being made moving forward, but the next time that I get to see you, I hope that you have both of those things for me that day. Today, I want to talk a little bit with you about equilibrium and torque, and then do a couple of practice problems so that, like I said before, we can just keep cruising and moving forward. So the last time that we had a snow day, I asked you to watch a video about starting to talk about equilibrium. So I just want to kind of get our brains back there a little bit and talk about that, and then we will find out kind of what that happens. So as I said, I had asked you, or I asked my students that you were listening to, define equilibrium. And as you may have assumed, as you may have thought, as you were watching that, and as my other students had assumed as well, equilibrium means that F net is equal to 0. And that is true. We know that that's true. But you may remember that I gave you that example of pushing the table. And when I had two students, one pushing this way and one pushing this way with the same force, we know that F net equals 0. And we can see from there that the table wouldn't move. It would be in equilibrium. But then again, if you caught the story that I was telling the last time, if I have one student pushing this way and the other one moves over here, in this case, F net still equals 0. But as you may get a sense from that, in this case, even though F net equals 0, that does not mean that the table is in equilibrium. In fact, it's not going to move in a straight line, so it still won't move in a straight line. But you may be able to tell from this that the table itself is going to rotate. It's going to come up like this and go down like this. So that's the interesting piece here, is that in this case, even though F net is equal to 0, it will experience rotational motion. And this is where we are focused for the next unit or so, is this rotational motion. So now, instead of just having equilibrium defined as we did before, we're going to write out a new definition for equilibrium. So equilibrium actually, full disclosure, has two conditions that need to be met. The first one is that F net must equal 0, okay? And that is what we've been saying since we started our year together, okay? And F net being equal to 0 basically means that there will be no translational motion. We haven't formally defined that before, but translational motion just means one-dimensional or straight line motion. So we talk about that in the x direction, the y direction. It could even be in the z direction, and positive and negative being right and left, up and down, that kind of stuff. All of the motion that we have talked about thus far this year is translational motion. The other condition that must be met for equilibrium, now here's the big reveal, here it comes. The other condition that must be met is that we have to be able to prevent what we call rotational motion. And the way that we do that is by having another quantity equal to 0. And that quantity is marked with the letter tau. So meeting our new Greek letter here, this is the Greek letter that in Roman letters is spelled T-A-U, tau, and it represents the torque. And we are saying now that just like we had F net equals 0, we are also requiring the torque net, or the total torque of a system, to be equal to 0. And when the net torque is equal to 0, then we have no rotational motion. And again, in order to have equilibrium, that means that there's no acceleration in the translational or one-dimensional direction, and there's also no acceleration in a rotational system. Okay? So this is a brand new word, a brand new concept for us, and we're going to define it kind of moving forward here, but I'm going to define it kind of step by step by step, okay? Everything that we do in this unit, it's kind of funny because it's got a nice little parallel to what we did in the first trimester and a half in physics. So everything that we did, we're going to kind of relive in a fast forward way in one unit, always talking about rotation. So basically all of the notes I give you, all of the concepts that we talk about the translational stuff because we understand that, and then we're going to kind of mirror it over in the rotational world. So we're going to start over here with the translational stuff and just kind of write down some things that we know. So we know that in order to get something to accelerate an object, okay, we need to apply a force. We'll say must apply a net force, F net, okay? And the bigger the force, the bigger the acceleration. These are not really big surprises. We talked about this a lot when we were kind of first building Newton's first and second law. You may recall an example that I gave you where if you have a big boulder and you apply a little force, you're going to get a little acceleration. A bigger force is going to give you a bigger acceleration. So I'm just going to write down example, and the example is pushing the boulder. All of the stuff in the left-hand column here is stuff that you already know. We've talked about this before, but I just want you to kind of have that so that you can use that to understand the rotational stuff as well. So in order to get something to accelerate in a rotational system, we need to apply a net torque. So we're going to say to rotationally or angular, or we'll say to, let's just say to rotationally accelerate. That seems like a better way to say that. Sorry. We'll bring that other word in a little bit. To rotationally accelerate an object, okay, we must apply a net torque. So it's kind of the if F net is 0, acceleration is 0. If F net isn't 0, acceleration is not 0. That was our translational business. Same kind of deal over here. In order to get something to accelerate rotationally, so that means just going around or moving around an axis. And I'll give you an example in just a second. Okay, to rotationally accelerate something, we must apply a net torque. And same way that we said before, the bigger the torque, the bigger the rotational acceleration. And you might be really eager and saying, well, how am I going to quantify rotational acceleration? Hold on to your hats. We will do that in a couple of days, I promise. But we're going to kind of take it one step at a time. So let me give you a concrete example of what this might look like, something that you have experienced, I am sure. The example that I have for you here is opening a door. Okay, so I just want you to imagine I'm going to look at the door from kind of above. So I've got the axis where the door is on its hinges, and then here is the door itself. So I'm kind of looking at it from above. So if you have ever watched a little kid try and open a door, so let's say we're pushing the door from below, they might apply a force over here, and it's kind of a sad situation because no matter how strong that little kid is, they're going to have a really hard time opening the door. Whereas if they just move over to the other side and they apply that same little kid force, they can get that door to open, right? And by open, I mean to rotationally accelerate, right? The door is sitting in one spot, so it's, we could say, at equilibrium until a torque is applied to it to get that door to rotate, okay? So how do I get a bigger torque? How do I get this rotational acceleration to happen? Well, so one way we could do it, so two options for bigger torque. One would be to increase the force, okay? If you're standing over here and you really want to get the door open, standing close to the hinges, you can do it. It just takes a really big force, right? So you can increase the force and that will get you the torque to get the door open, to push it, to get the rotational acceleration to happen, okay? The other option, option number 2, is to apply the same force but just to move over further away from the axis, further away from the hinge. And what we kind of the technical term for that, the way that we describe that, is to say that we increase the radius. Okay, increasing the force or increasing the radius will increase the torque. And by increasing the force or the radius, and thereby increasing the torque, we can get the object to rotate, or we can attain rotational acceleration. Okay, so that kind of hopefully gives you a little bit of a concrete example of what I'm talking about when I say rotationally accelerate. So let's define torque a little bit more, maybe a little more formally here, so that we can have something to talk about in a little bit more concrete fashion. So torque, as I had marked before, is marked with tau. That's a capital tau in the Greek alphabet, okay? And torque is equal to, and this is how it's written in your textbook, this is how it's written on the equation sheet as well, R, which stands for radius, okay, times force, F for force. And these two things should not surprise us given our just example that we just did. The key here, and the other piece of this, is that the force and the radius must be perpendicular to one another. Okay, the force and the radius must be perpendicular to one another, and those two things multiplied together will give you the torque. Now, a couple of pieces here. Let's look at some units just to kind of give ourselves a handle on what's going on. Radius is measured in meters, force is measured in newtons, okay, and torque is measured in meters times newtons or newton meters. And a lot of you are like, oh my gosh, I've seen that before. I know that that's a joule. Okay, so here's the game. It's a little bit funny. This is not the same thing as joules. So when you start to play with vector multiplication in mathematics, so you may do this in calculus, you may not do this until you get to like a linear algebra or something like that, you'll find out that multiplying vectors, and by vectors I mean things that have direction like radii and forces, result in different kinds of quantities than do multiplying scalars or things that don't have a direction. So for right now, what I'm going to ask that you do is that just kind of sit back, take a deep breath with it, and say, okay, Miss K, I got this. I'm just going to call this a meter times a newton or a newton times a meter. This is not a joule. It's not a measure of energy. It's a different kind of quantity, but it's measuring a ability for something to rotate. Okay, so that's just kind of a heads up that I want to give you, because I always have students who are like, oh, I want to say it, but it's not quite what you want it to be. Okay, so that's the first thing that I want you to know. The other thing to keep in mind is that force and radius have to be perpendicular to one another. So when we did work and we were talking about force times distance, the force and the distance had to be parallel. You may remember that in the textbook it said F times D times the cosine of theta, which gave us that parallel piece. In this case, when we're talking about torque, if we think about opening that door, if you applied a force, so this is my radius here, so here's my door, there's my radius. If I apply a force in this direction, that is for sure not going to open your door, right? In that case, the radius and the force would be in the same direction, and so you're not going to get any torque. I'm going to go ahead and draw another door down here just so we can kind of look at some different cases here. So again, there's my hinge. Here's my door. Okay. If I was going to try and get the maximum torque to open my door, I'm going to apply a force at the very edge, right? That's going to give me my maximum R. Okay. And the force I'm going to apply is exactly perpendicular. Okay. That's how I want to open a door. You know, because you've been opening doors all your life, right, that you apply a force towards the edge, and that's going to open it up most efficiently. If I instead apply a force in this direction, even if it's the same size force, it's not going to open the door quite as efficiently. And that's kind of a funny thing to think about, because why would you push on a door in that direction? But, sometimes that happens, like especially if you're backing into a door, something like that. But really, the only part of the force that's going to give you a torque is this component right here. Okay. And so the more perpendicular you make that force, the more torque you're going to get. Okay. So that's why we say that the force and the radius have to be perpendicular to one another. All right. So those are the main components. If we were going to just kind of make a list here of the things that we cared about, we care about number one, the radius of or the radius at which the force is applied, or we'll say the distance between the axis of rotation, or where the system will rotate. So in the case of the door, it's pretty obvious that that's going to be where the hinge is, okay? Distance between the axis of rotation and the point, I'm going to say, at which the force is applied. That's one thing that the torque depends on. Another one, as you may guess, is the force. So the size of the force that's being applied, okay? And then number three is the angle between the force and the radius. And we'll just kind of put a parenthesis in here just to remind ourselves that we can maximize the torque when the force is perpendicular to the radius, okay? Anytime, so that's one little piece of information, anytime that torque net, so just like F net, or the net force was adding up all the forces acting on something, same kind of deal with torque. We're going to add up all the torques. If the net torque is not equal to 0, okay, that means that we have a rotational or angular acceleration. Rotational, angular mean the same thing. They're just kind of interchangeable. We will end up using the word angular a lot this unit, so that's why I wanted to kind of introduce that to you. Okay, so that's one thing to note. Okay, and the other thing that I want to make sure that you're aware of as we are moving forward, I'm going to go way back up here just so that you can see the parallel here. When we talked about F net, when we were talking about displacements and velocities and accelerations, we always talked about things being positive or negative. And that's very natural for us to say that positive is going to the right and negative is going to the left. That's just kind of in our kind of in our schema that we're used to. When we're talking about things rotating, we have positive and negative rotation as well. And this one's a little bit less intuitive, but it's no different, and it's no more, wrong or right. It just is. So I just want to kind of give you a sense of that. So if you've got your axis, right, and we're talking about rotating things, if I've got my door here and I apply a force this way, then I'm going to get a rotation that's in this direction. We call that counterclockwise. As you would know, looking at an analog clock, right? The clock hands would normally go from here, it would go down. So going up would be counterclockwise. And counterclockwise is positive in our kind of scheme of positives and negatives. Okay. Whereas if I had a force that was pushing down in this case, that would result in a rotation in the clockwise direction, and clockwise we call negative. So it's a little bit funny because counterclockwise kind of sounds like it should be a negative thing, but it's actually positive. For those of you that are familiar and know and love the unit circle, this seems a little bit more natural because going from the x-axis moving up, that's going to be a positive angle. So that's kind of where the positive and negative definitions come from. So again, going up from here, counterclockwise, and that's going to be positive, and going down is clockwise. I'm just going to write that down here, clockwise, and that is what we're going to call negative. So those are the kind of basics of the definitions of this new funny thing called torque. We're going to get to know lots and lots of new and interesting terminology as we go through the rotation. I'm going to give you a couple of quick examples to look at and to work on with me so that you can feel confident moving into your homework for this lesson, and then we will be done for the day. So here we go. So here's the first example. This is from my ranking task stuff, but it's not actually a ranking task problem. Take a look at it with me here. So you've got 5 identical keys suspended from a balance. So you've probably seen something like this. Like when you were in elementary school, you may have seen this, and it's actually a really nice and powerful tool for learning math, but it all comes from physics. And that's why I wanted to share this with you, because it's kind of cute. Okay. So anyway, it's held horizontally. You can see the person here that's holding on to it so that it doesn't go anywhere. There they are. They're holding on. Okay. 2 keys on the left are attached, balanced 6 centimeters from the pivot point, and 3 keys on the right are attached 5 centimeters from the pivot point. The first question says, what will happen when the person lets go of the balance? So I want you to take a look at that, pause for a second, see if you can figure out what's going to happen. And then we'll kind of think about what forces are acting. So we are winding ourselves way back to the beginning, to Newton's first and second law. We really, without saying it explicitly, are doing Newton's first law for rotation right now. So if we look at the forces that are acting, there are actually 4 forces acting on the balance beam, on this thing in this story. Okay, so let's assign those forces. The first one is going to be the keys pulling down here. I'm going to call that F1. Okay, the keys pulling down there. Another one would be right over here, the keys pulling down here, F2. And if those are the only 2 forces acting, then by golly, that thing's just going to fall straight down, right? You can also maybe assign a force to the whole bar pulling down. I'm going to call that balance. I'm going to call the mass of the green thing negligible for this problem, just to keep things simple. And so I'm going to give just actually one more force. And there's got to be one other force, right? Otherwise, the whole darn thing's going to fall down. And that's kind of a force from this pivot point here. Okay, so the force from the pivot point right up there. So we could say that all of those 3 forces have to add up to 0. Otherwise, there's going to be some sort of translational motion. It's either going to fly up in the air, or it's going to fall down in the onto the ground. Okay. The thing we really care about in this question is what's going to happen when our handy dandy hand over here moves. Okay. And so we can think about that in terms of the torque. So I'm going to go ahead and write out a torque net equation. You may have a gut feeling, you may have a sense of what's going to happen. You may have even already done the math, but I want to just kind of give you a sense of how we can do this in kind of a very rigorous and explicit way. So we can see that the net torque acting on the system is going to just be every single torque acting. And we get this equation from the exact same place that we get any other like F net, where we're just going to write down all the forces. In this case, though, we're going to write down all the torques. So I'm going to have torque 1, and I'm going to have torque 2, and I'm going to have torque P for pivot point. Now, for each of those cases, I've got the force times the distance, right? I guess in my equation that I gave you before, I had the R and then the P. I apologize. I'm going to go ahead and keep writing it as F and then R just for this one. Just to kind of give you a sense. I'm not going to say that this is equal to 0 because it might rotate, and if it rotates, then the net torque doesn't equal 0. Now, I'm just going to kind of keep plodding along here and see what we know. So I know this distance, I'm going to write these as R1, R2, and RP, just because I've got, I love my subscripts. So R1, I know that's 6. And R2, I know that one, that's 5. How about RP? Oh, and how do I know these? Remember, the R is the distance from the pivot point to the force, right? From the pivot point to the force. So that's going to be that 5 and that 6. The distance from the pivot point to the pivot point, that's 0. Okay, this is a really powerful thing, and we'll use this a lot in the next few days in terms of solving problems. There is no torque from this pivot point because the force is acting at the same point as the axis of rotation. So that's super helpful. So if I've got a force of, I'm going to say 2 keys worth of forces acting 6 away, and I've got a force of 3 keys acting 5 away, which one's bigger, friends? 2 times 6, oh, that's 12. 3 times 5, oh, that's 15. Now we know which way that thing's going to go. If we're going to be really good and kind of do all this very rigorously, a force pulling down F1 is going to cause a positive torque. Okay, why positive? Because it's going to cause a rotation in the counterclockwise direction. Okay. The F2 torque is going to cause a clockwise rotation, okay, which is negative. This one's bigger. So hopefully your gut feeling was telling you that the F2 force, or this set with 3 keys here, is going to win out. We'll say it's going to pull harder and it's going to have more torque. Maybe that's the really good way to say it, right? And so it is actually going to apply a bigger torque, and it's going to cause it to accelerate in the negative direction. I'm going to ask you a part B. It's not actually written on here, but it's in my head, so I'm going to ask you. So part B, the next question that I'm going to ask you is, how can I adjust the keys to make it balance? So take a minute and think about that. See if you can figure out a way that you might do that. Okay. So really what you're trying to do here now is to get your net torque equal to 0. All right. So the torque from FP is already 0. So we need to get the torque 1 to be equal to torque 2, right? Equal in magnitude, opposite in direction. That will lead us to an equilibrium. So one way that you might do this, and again, there are multiples in this case, one way that you might do this, a pretty simple way, is to leave the keys for F1 where they are. So you've got 2 keys, And I'm kind of doing a hand wavy thing here. I hope it's not upsetting you. We'll call this like mass. If these each have a mass, right, then the force of gravity is pulling them down. I should have said this explicitly before, but I'm just, because they're all the same mass key and we don't really care about gravity, I'm just calling all that force a force of 2 and this all a force of 3. So I hope that that's okay with you. So that's 2 of force of 2 times the distance of 6 would equal a force of 3 times the distance of 4. So as a simple way, again, not the only way, but a simple way would be to just move these keys over. And if they hung right here, then we would have a system in equilibrium. Okay, so that's just one kind of example of how you might get something to balance and how you might deal with the situation. I'm going to do one other quick example with you and then we'll be done. And this is a real live ranking task for you here. So let's take a look at the question and then I'll kind of get you started and put an answer up at the end to see if you agree with it. So we've got a 2-meter long massless rod. That's nice. We'll talk about massive rods in a couple days here, but we're just talking about this thing. We're trying to keep it as simple as we can. So we're just making this long stick here. It's got no mass. Life is good. Okay. It's supporting a 12 Newton weight. So this weight here, wherever it's sitting, is 12 Newtons. Okay. The left end is held into place by a frictionless pin. So there's a pin here, which means that it's going to rotate about that spot. And then something is holding it up with a force over here. Okay. And that force in some cases has moved. So the question is, or the task is, I should say, to rank the magnitude of the vertical force applied so that each system is at equilibrium. Okay. I'm going to let you work on that one. We will talk about the answer to this one at the very beginning of class on Wednesday. Please make sure that you have some answer written down, some answer that you believe in and that you can justify written down. I may collect it. We'll see. Let's assume I will so that you actually do it. All right. I hope you guys have a fantastic, safe, great snow day. Please make sure you get some work done and take a little rest as well. Take it easy, you guys.